Hello everybody, welcome to our lesson. Today's topic is the magnetic force on a current carrying conductor. So this is the situation when a current carrying conductor or a wire is located inside the magnetic field. This is the goal of the lesson. At the end of the lesson, you'll be able to use the second right-hand rule, describe and calculate the force acting on a current carrying conductor. Now, do you remember this demonstration? If a current running through a wire exerts a force on a magnet, you might expect the opposite to be true as well, that a magnet exerts a force on a current running through a wire. And it does. Pay attention to this demonstration. A conducting rod will not produce a magnetic field until a current flows through it, as discussed in before. The conducting rod in the first picture will not interact with the static magnet field of the U magnet, since no current flows through the rod. However, if a current starts to flow through the rod, a magnetic field will be formed around it and the wire will experience a force due to the static magnetic field as shown in the second picture. The direction of the magnetic force will be reversed when the current direction is reversed in the third picture. The direction of the force from a magnetic field on a current running through a wire will be perpendicular to both the magnetic field and the current. Now let us look at the force exerted on the wire in detail. When the current carrying wire is placed in an external magnetic field, the magnetic field produced by the wire interacts with the external static field. The magnetic field strength will increase in the regions where the external field and the wire's field are in the same direction, and it will decrease in the regions where they are in the opposite directions. So the wire will deflect towards the weaker magnetic field regions as shown in the picture. Now, the direction of the magnetic force is given by the second right-hand rule. This one helps you keep track of three directions: the direction of the magnetic field, the current, and the force. Here's how to use the second right-hand rule. Point the fingers of your right hand along the direction of the lines of the magnetic field and indicate the direction of the current with your thumb. The force on the wire is in the direction in which your palm would push. This describes the direction of the magnetic force. But what about its magnitude? There are three factors that affect the magnitude of the force. First, it's current in the wire, that is I. And the stronger it is, the stronger the force is. Second, there is the length of the wire running through the magnetic field, that is L. And the longer the wire is, the stronger the force is. Third, there is magnetic field, B, and the stronger B is, the stronger the force is. But the force also depends on the angle between the wire and the magnetic field. This picture shows the variation of force with the angle. When the field lines R and wire are parallel to each other, the wire experiences no force. The force is strongest when the wire is perpendicular to field lines. At other angles, the force is proportional to sine alpha. Why force is proportional to sine alpha? Because the closer to perpendicular the current is with respect to the magnetic field's direction, the stronger the force is. That's why we use sine alpha. Its maximum value is 1 when alpha is 90 degrees, and its minimum value is 0 when alpha is 0 degrees or 180 degrees. So finally, here comes the equation. The current carrying conductor will exert a magnetic force from a magnetic field, and this force is described by this equation. Force is equals to current multiplied to the length of the rod inside the magnetic field and magnitude of the magnetic field and the angle sine alpha, angle between conductor and a magnetic field. So this is the end of the lesson. If you like our lesson, please subscribe and share.